Welcome to Precalculus with Ms. Nisker. Today we're going to look at rational exponents. So we're going to fill out this worksheet. So hopefully you've had a chance to print it off or to pre-copy it so that we can talk about rational exponents in power functions. So I'm going to do some reading and some filling in. So as we start to look at this, we've got, although we have considered power functions x to the n that have positive integer exponents, any function in the form of fx to the a, where a is any real number, not just a positive integer, is considered a power function. An important special case of this kind of power function involves rational exponents. Okay, so we're going to recall that a rational number is a fraction. And a fraction is the quotient of two numbers. So anytime I see the word rational, I should think of the word ratio, and anytime I think of the word ratio, I should automatically think fraction. And at this point, some of us cry because we're like, I don't want to deal with fractions, but we do have to deal with fractions on a regular basis. And I understand that because I'm not one to share, so fractions are not always my friend. Okay. So the functions like x to the 1/2, x to the 3/5, x to the negative 2/3, and so on would be considered power functions with rational exponents. So how do we work with those exponents? Well, we can convert them to more recognizable form using familiar exponent rules. So we're going to start with x to the 1/2 as an example. So let's see if we can actually prove that x to the 1/2 is equal to the square root of x. So we're going to start with the assumption that x to the 1/2 is equal to the square root of x. Well, if I think about this and I just square both sides, it's real easy what's going on here. The square root and the square, they undo each other, so we're left with just the x on the inside. Here, I end up with x to the 1/2 times 2/1. And remember, when I'm multiplying fractions, I multiply straight across, so that ends up being a 2/2, and that's hideously ugly. So I will make sure that we write that just a hair bigger and better, so you can see both of those 2's, which is really just x to the first, which is x. So now we've proven that, because anything to the first power is just itself. Now, this is actually true for any integer n. So if I have x to the 1/n, this is really equal to the nth power of the nth root, sorry, not nth power, nth root of x. Okay, that's because what you don't see over here is there's really a 2, but square roots are so common that we don't write the 2 anymore. We just write it as this symbol. I remember what it means is we're looking for two factors that are exactly the same all the time. So the denominator of the rational exponent corresponds to a root or a radical. Now, in the 80s, we had an issue with the word radical because we used it to mean something else, but all radical means is something that looks like this. Okay, so you'll hear radical and radicand. So what about x to the 3/5? Okay, so when we start looking at x to the 3/5, we've got to break this up. So if I break this up into x to the 1/5 times 3/1, I get x to the 1/5 raised to the power of 3. Excuse me. So this means that I'm looking for the fifth root of x cubed. Now, neat square is kind of weird, so this is not the only way we can break this up. We could break it up the other direction where we put the 3 first. And that changes things ever so slightly because we end up with the fifth root on the outside and the x cubed on the inside. So when I start looking at this, and we can expand it to the previous rule, so we've got x to the m divided by n is equal to the nth root of x to the m based on this property above, which is why we have the line, the 1 to refer back to it. Okay, so the numerator of a rational exponent corresponds to a power inside. So this one is the most used. Okay. So it corresponds to a power inside. In fact, I'm going to make that really big so that I can remember it. Inside. INSIDE. You spelled it right. A root or radical. Now let's track x to the negative 2/3 to come up with a basic rule, and let's consider the simple problem of x to the negative 2 first. Again, we can be clever about how we write the negative 2. So we're going to start with a couple of things. We're going to start with x to the 0 minus 2. Those are powers, those are exponents, so they should be tiny. But this comes from our exponent rules of x to the 0 divided by x to the 2. So I call this my change of position. I call that change of position. So x to the negative 2, change position. So if it was in the numerator, it goes in the denominator. If it was in the denominator, it goes to the numerator, so we can make it positive. Okay? And applying the familiar exponent rule in reverse. Oh, I did all the steps horizontal, sorry, instead of vertical. And then, of course, the key here is the important, very important rule to remember. Anything to the 0 power, anything, not anything, anything. Equals 1. Anything to the 0 power equals 1. So what we have is that this is x to the negative m divided by n is just equal to 1 over x to the m divided by n. So a negative exponent corresponds to a reciprocal. I have to be careful because I know we just came out of doing functions, but we want to make sure that we're aware of that. So we're going to do 3 examples, and then the rest of the work on the back is left for you. So when I write the 3 rules here, I'm going to write the power function with exponent of 1 to the n. So x to the 1 over n is equal to the nth root of x. The power function with the exponent x to the m is m divided by n, sorry, x to the m divided by n is equal to, we're going to put that on the outside for the root, on the inside for the exponent. And when I have x to the negative a, I'm going to rewrite it as 1 over x to the a. So those are my rules. And I'm going to copy those rules. Now for those of you using the same sheet of paper, you don't have to worry about copying those rules, but I am going to copy those rules onto the top of the back of my sheet so that I can have it when I start working on these problems. It's an A, not a 9, so I do have to watch out for that. And that is working with rational exponents. So you're going to do those 6 problems, and then you're going to complete some tables and some graphs and talk about some key characteristics. Thanks, guys.